So yeah, we're going to continue proving the Erdős theorem. We'll just sort of restate it, or at least the kind of version of it that we're going to prove. So I want to show that for every r at least 2 and t at least 1, these are integers, and epsilon positive, that's a real number, there exists some number n naught depending on r, t, and epsilon, such that if if P has n vertices where n is at least is n naught RT epsilon, if it has at least n vertices, or has n vertices where n is at least that number, and the number of edges is at least r minus 2 over r minus 1 plus epsilon n squared root 2. Then G contains copy of this complete multi-partite graph KTTT dot dot dot, where the number of parts is equal to r. I should probably just come up with some notation for that, but yeah, let's just write it like this for now. And yeah, as we said, this implies the Erdős theorem, because if you contain like a KTTTT, etc., if T is large enough, then you're going to make that it will contain any graph of chromatic number R on at most, let's say, T vertices. So prove so yeah, let P be such a graph. Well, actually, what do I mean by such a graph? Like, I've got this kind of implicit, this n naught of RT and epsilon, which I haven't really defined. I mean, if I was doing this super carefully, maybe I would define RT, RT epsilon, let n be at least that, let G be such a graph. But like, it's actually going to be really painful to write down an expression for this. So basically, we're going to discuss when it comes up during the proof, we'll discuss kind of how big this needs to be. So we kind of postpone yeah, the kind of discussion of what is this n naught thing later. Basically, like at some point in the proof, we're going to say, this some inequality would hold if n is really, really large. And then at that point, we'll, that kind of defines how large this has to be. Okay. So what we did last time, if we showed that if you've got a graph with like a large number of edges, you can reduce to a subgraph with a large minimum degree. So that's going to be the first step. So by the lemma from last time, and you'll remember that the lemma from last time had some like a square root in it and stuff. We don't really care what that expression is in some sense. So I'll just say there exists some, C depending on R and epsilon, such that G has a subgraph G prime with the minimum degree in G prime being at least. So we take basically the same thing as we have for the number of edges of G, so R minus 2 over R minus 1. But we're going to take epsilon over 2. So plus, instead of plus epsilon, we need to throw away a little bit. And then we take number of vertices of G prime minus 1. And the number of vertices in G prime is not too small. So it's at least C of R and epsilon times N. The last time we gave like a very specific value for this. So there was like apply the lemma from last time where there's like an alpha in that lemma. So this would be alpha. And then there's a gamma. Gamma would be this, which is slightly less than alpha. And then the CR epsilon would be whatever you get by plugging in this for gamma and this for alpha. So these are the properties we have for G prime. The point is we can, if you have a graph on n vertices with high number of edges, we can restrict to a subgraph with a high minimum degree, as long as you give away a little bit. So replace the epsilon by an epsilon over 2 or something. And you can do that in a way that, I mean, actually, to be honest, you might be throwing away 99.999% of the vertices, and you've got like 0.0001 left. But you still got, but it's still like something that grows with n. As n goes to infinity, I can make this as large as I want. So what we're going to do is we just ignore the whole rest of the graph, and we're just going to find the copy inside of G prime. Okay, let's draw a picture just to illustrate how we're going to build this thing. So, to be honest, I feel like a natural strategy is, okay, if you're building up a K, T. So this is not quite the strategy we're going to follow, but you might want to say, okay, let's build the first part, and then let's build the second part. And I need all of these T things to be joined to all of these T things. And then once we build the second part, let's start building the third part, right? I need that to join to all of this, and that to join to all of this, and so on. Turns out though that you might just get stuck, right? After I built, say, 2 parts, it's hard to now guarantee that there's going to be T vertices that are adjacent to everything here and everything here. Basically, if I somehow get unlucky and I've started in a bad place with a bad set, sets here, I may not be able to continue. So somehow it's useful, instead of doing this, what we're going to do is start with the first part being way bigger than we need. So way bigger than T. So there's a bazillion vertices here. Now when I go to build my second part, it's still going to be a lot bigger than T. Yeah, what I'm going to want is, so this size is going to be kind of smaller than this one. And what we want to try to find is kind of a blob here that has, so these have the same size. And you've got all the edges between these two. And then when I make my third thing, I'm going to try to find a bunch of vertices that, where there exists a set here and there exists a set here, such that I've got so let's say these 3 kind of blobs are the same size. you know, they don't really look like it. So like in every step, basically, I'm gonna build a complete multipartite graph bigger than I need. So that in the next step, I have choice of where I can place the next set inside of each of these. And somehow that's gonna be fairly helpful. Okay, so and each time then, you know, I just completely throw away this stuff, all this stuff I don't care about. Right, and I just keep tunneling, you know, further and further down. But it sort of helps to start with a bunch of room, a bunch of extra space, and then build from there. Okay. Let's let me show you what let's make this kind of more formal. So let T sub R equal to T. So basically T sub R indicates like that's the size I want to find for like a complete R part-type graph. Like I want the parts to be of this size. When the number of parts gets to R, I want this size. And then for S between 1 and R minus 1, let TS be so leave it as 4 over epsilon times T S plus 1. And then because that might not be an integer, we take the ceiling. So like this indicates my goal for the last step. Like when I have R parts, I want them to have size T. When I have R minus 1 parts, I want them to have T sub R minus 1 size. When I have R minus 2, like all the way down to the to 1 part. So we want to show that for all between 1 and so S between 1 and R, G has a complete S part-type graph. It's a subgraph with parts of size TS. And then applying this to the case that S is equal to R gives us what we want. We're going to build this up iteratively, basically. I mean, we could say this, it's kind of by induction in some sense. So we're basically using induction on S, where the case S equals 1 is kind of trivial. Just pick any set of T1 vertices in G prime. Actually, so here when I said G, I actually meant G prime. So everything's gonna live inside of this graph of high minimum degree. So yeah, that should have been a prime. And like, so this kind of, in a very mild way, requires n to be large. So I mean, Because if n is too small, maybe there aren't that many vertices, but yeah, we can do this. As long as n is at least T1 over this CR epsilon thing. And yeah, this is just going to be a T1 is just a function. It depends on T and R and epsilon. So this is just a constant. So this is a constant depending on T, R, and epsilon. All I'm saying is to do the first step, you actually need that many vertices, but that's a pretty weak condition, right? Any questions so far about what the plan is or what we're doing? Yeah,
Sorry, is that T subscript, is that a plus or a minus there?
that's a plus.
Okay.
So it's kind of weird, it feels a bit backwards, but we define like the biggest one for like the biggest index first, and then we define the next smaller index, all the way down to one.
Right.
Yeah. Okay. Questions at this point? Okay, so now we're going to do the inductive step. So suppose S is at least 2, and let say B1 to be B sub S minus 1, the parts of a complete S minus 1 partite graph, partite subgraph of G prime, where each of these sets has size exactly E sub S minus 1. And let's let B be the union of the BIs. So yeah, we've got these, this B1, B2, BS minus 1. So these are possibly, fairly large sets that where I know that all the edges between any pair of them must exist in the graph, in G prime, in fact. So what we want to extend this to from S minus 1 to S. So what I want to do is find, a set of TS vertices where, they have a sort of, there's a set here of size TS, like, all of these kind of previous parts, I've got a set of TS vertices in each of them where this thing is adjacent to everything in all of those sets, right? Okay. What we should first do is kind of let's like some vertices in the graph are just completely useless for this purpose. Like there may be vertices in the graph that have too few neighbors in one of these parts, and then we can't use them, right? So let's first Yeah, let's define a set which is kind of the useful vertices, like the ones that have at least T sub S neighbors in every single part. So I'm gonna let W be the set of vertices which are in G prime and not in B. So they have to be literally kind of, genuinely outside of what we built so far. Such that I don't think I've defined this notation yet, but so this is the neighborhood of the vertex B. So this is these are just all the vertices that have an edge to B. So and I'm putting this subscript G prime just to say we're looking at the neighborhood of that vertex in G prime. And I want this intersection of the neighborhood in BI to be at least TS for all I from 1 up to S minus 1. Like I say, any vertex that doesn't have this property is quite useless to us. We can't actually, we just can't use it. So W is kind of an important set of vertices here. Questions? So, what we're going to want to do is show that this set W is very, very large. And the thing is, actually, let's think about this, right? But if this set W is super, super large, well, for each thing in W, right, it has a certain kind of neighborhood in each of these sets. It has at least T sub S neighbors. Let's say we even forget about most of those neighbors and just say, okay, for each vertex in W, just pick a specific set of TS neighbors in each set, in each of these things. Well, by pigeonhole, I've got a bazillion vertices in W. Like there's only a finite number of choices for what its neighbors could be here. And there's a finite number of choices for its neighborhood here, and here, and here, and here. So if I've got a huge number of these, then there's going to be repeats. There's going to be some vertices that have actually the same neighborhood on all of these sets. And those are the ones I choose as my. So there's going to be, eventually you'll get at least TS of them that have the same neighborhood in all of these sets. And then those are the ones I pick as my TS things. So basically I want to show that this set W, that the size of W grows as n goes to infinity. That if n is big enough, by pigeonhole I can find these things. We'll do that formally at the end, but yeah, let's show that W is large. This comes down to more double counting. So let's double count non-edges from B to G prime minus B. So on one hand, the number of non-edges A to the complement of B. Well, on one hand, anything that's not in W must contribute a fair number of these non-edges. So like, if something is not in W, there's one of these blobs where it has very few edges to it. But then there's one of these blobs where it has many non-edges to it. So for every vertex that's, let's say, not so that's not in W and also not in B. It's going to contribute yeah. So in fact, I can make this a strict inequality. So each of these neighbors, or each of these vertices, yeah, there's one of these sets for which it has fewer than TS neighbors. This set has size exactly T sub S minus 1. So it must have more than TS minus 1 minus TS non-neighbors in that set. So yeah, this is the size of like a BI or NEI. And this is like, yeah, it doesn't have this many neighbors, so it has at least that many non-neighbors. Okay, so this is at least number of vertices in the graph minus B minus W times 4 over epsilon TS minus 1. And that's because of how I define, or sorry, TS. Because this is it's this is the ceiling of 4 over epsilon times TS. So sorry. It's that and then minus TS. Oh, sorry, I want to write this in yet another way. I actually want to write this as this is TS minus 1 minus epsilon over 4. So sorry, I actually want to get this in terms of TS minus 1. But all of these different ways of writing it, they are correct. So yeah, this is TS is at most. So I'm using that. Okay, so this is a lower bound on the number of non-edges. Well, we're going to combine this with an upper bound. So now I'm going to count non-edges from B to G prime minus B. I can do this. So a way I can upper bound this is using the minimum degree condition. Right? Because like every vertex has degree at least this. So literally, every vertex could not have a super large number of non-edges incident to it. So all I'm going to do here is take B and say that each vertex only have degree at most this minus the minimum degree. So I guess for each vertex in B, the total number of non-edges incident to it cannot be more than this. Because the number of edges incident to it is at least delta. Which is then at most b times 1 over r minus 1 minus epsilon over 2. And then times number of vertices in G prime minus 1. We're plugging in the lower bound we have for the minimum degree from over there. Which is in fact equal to s minus 1 times t sub s minus 1 times the same stuff as before, so 1 over r minus 1 epsilon over 2 b of g prime minus 1. So I'm just writing out how big is b. And yeah, S is at most R, because otherwise we would have already stopped. Like we only do this for S from 1 up to R. So this is at most R minus 1, T sub S minus 1, 1 over R minus 1 minus epsilon over 2, B of G prime minus 1. So all I've done is place this with the S with an R, which is like T sub S minus 1 minus epsilon times R minus 1 over 2. So I'm just bringing in this R minus 1 into this thing with fractions. And then number of vertices in G prime minus 1. Actually, let's go back to this one and just write something here. And then maybe it'll be clear what's going on. So if I factor out a TS minus 1, we got 1 minus epsilon over 4. So in some sense, if I want to compare this to this, so I want to get that W is fairly large. And this is kind of getting it to me, because it's like saying, okay, the number of non-edges is at least this, which is, so it's, if we ignore this, okay, this is basically the number of vertices in G prime, and then maybe minus W. This is just a constant. It's S minus 1 times TS minus 1. This is kind of irrelevant. What we've got here is a lower bound that looks like, so both of these have a TS minus 1 in them, they can kind of cancel. And basically what I want to say is that like, this is kind of, but let's say W was not large, then these things are pretty much the same. If W was, say, bounded by a constant. These are the same, but the thing is this, 1 minus epsilon over 4 is a lot bigger than 1 minus R minus 1 times epsilon over 2. Like, I mean, in the worst case, maybe this is like epsilon over 2 or something, right? So this is bigger than this, which kind of tells you that this needs to be kind of linear in terms of the number of vertices. Like, in order for this quantity to be less than this one. We can do the algebra, but it looks good. what I'm trying to say is that. So let's put these two inequalities together. S minus one minus epsilon or minus 1/2.
We get actually strict inequality, don't we?
Yeah. And V of G prime minus 1. And if you solve this for yeah, so this cancels, the TS minus 1 on both sides cancels. We solve this, so let's put, I'm gonna put the W on one side and everything else on the other side. So I'm gonna put it on the kind of positive side, so it's like 1 minus epsilon over 4 times W, strictly greater than. So it's like multiplying here and then putting it to the other side. So let's call this like, oh. I'll just write it out, so.
Get a negative on that.
Yeah, you're right, thanks. Yeah. So B of G, 1 minus epsilon over 4, and then minus the size of B, 1 minus epsilon over 4. Some of this stuff with the B of G things cancel. Like there's a 1 and a 1. Those are going to cancel, and kind of I'm left with this times B of G prime. And then let's just call everything else some function depending on the constant, depending on, let's say, R, T, and epsilon. Which it is, right? Because what am I subtracting? Actually, it's pretty much just size of B times 1 minus epsilon over 4. Size of B is S minus 1 times T sub S minus 1. So this, the size of B is just a constant that depends on T and S and R and stuff. So is this. There's this like little -1, but actually that helps us. So because it's a minus minus, so it actually improves the bound. So we can even throw away this -1 here. But really the stuff that really mattered, oh sorry, this should be fine. The stuff that really matters is the constant, you know, there's a positive constant in front of the B of G. So, and then if we can solve for W further by dividing, right? So basically W is at least some constant depending on all of these other parameters times n. And then if we let n be big enough, then we're going to get a bunch of vertices which have the same kind of neighborhoods in these sets just by fishing pole. maybe to, just to finish that off. So choose and large enough that we get that W as size at least. So I can be a bit, a little bit, well, wasteful here. I want to be, let's say at least this to the S minus one. Let's and a strict inequality and make that TS minus one. And this implies that there exists TS vertices in W with exactly the same neighborhoods in the sets E1 up to B S minus one. So why is this? It's because if I take a vertex, how many ways are there to choose the neighborhood into B1? Well, B1 has that size, so there's two to that many number of neighborhoods. And I'll do that for all of the BIs. There's that many choices. And if it's, so this is to get that there's T of S that have all the same one. So like, if I didn't have this would just show me that there are two vertices that have the same neighborhood. But with this, I actually get TS of them with the same neighborhood, because if each neighborhood only appeared TS minus one times, then W would be almost the quantity, right? And basically that gives us an S-part type graph with parts of size TS. And that's because, remember, it's important I define W to be vertices that have at least TS neighbors in all the parts. So having all their neighborhoods be the same isn't quite enough. You need them, all the neighborhoods to be the same, and all of those neighborhoods to be big. But W has that property, right? It's all the things that have big neighborhoods into all the sets.
When we're saying the same neighborhoods, we're not actually looking at their neighborhoods, we're looking at some fixed choice of TS vertices for them, right? Like.
Yeah, I kind of said that before, but now I'm gonna just decide not to even care about that. We could just make their neighborhoods actually the same. Because, I mean, there's only that many. I guess if I was to choose a specific set, I would have like a slightly better bound. I would have something like T, like this, choose this to the S minus one. But if we're even more lazy, we can just say they've got exactly the same neighborhoods. But yeah, before I was kind of saying for each of those vertices, just choose TS of their neighbors in each of the things, but we don't even need to do that really. Yeah, so that is proof because, you know, basically we're done by, you know, considering the case where S is equal to R. It's kind of we really had to get our hands dirty with this proof. It's like, I always love these proofs where it's just like a slick argument and, but yeah, we had to really construct this thing. And like, unfortunately, like this, so you might wonder, like, is this whole business about n being large and having an epsilon and like this limit thing, like, is that really necessary? And the answer is, it actually really is necessary. I think you'll have on your third assignment, asked you to construct an example of a graph where basically the chromatic number is 3. And the extremal number kind of, so we know if chromatic number is 3, the extremal number should grow kind of like n squared over 4. But there's going to be like an extra term, which is like kind of like some constant times n to the 3/2 or something. But like, as if n's large enough, this is always at most epsilon n squared or something. So this still does have, like, the growth rate of this is still like n squared over 4, but there genuinely can be a lower order term. So it's not like equal to that, right? There is like some other term that's being added there. So yeah, that's, like I say, that's on your third assignment, I think. Any questions about any of this? Okay. So yeah, then on next time we'll talk about extremal numbers of even cycles, and then on Friday there's actually like a guest lecture, I guess. So on Friday we'll keep the desks this way and we'll watch it like on the TV. She's going to be zooming in from somewhere else. Okay. Let's see what happens.